So I'm actually going to be talking about only some cluster science because between submitting this talk and seeing the conference program, I think I sort of overextended myself a bit in the title. But first of all, thanks very much for the organizers for inviting me to give this talk. It is cluster related. I haven't seen very much cluster stuff, so do bear with me. A lot of the talks following the session are going to be on the galaxy evolution, so I'm not going to touch that at all. I'll leave that to other speakers. But firstly, why do we care about galaxy clusters? So pretty much everyone in this room who works on the science, you're going to fall into one or both of these categories where you're either interested in cosmology, so universe, universal scales, what it's done, where it's going, or you're dealing with some sort of astrophysics. And obviously, with astrophysics, there's a wide variety of scales involved in this. But clusters are important because they bridge these two. And this is sort of shown here where you can see where clusters lie. So they're formed at the nodes of the cosmic web. So for example, if you think about cosmology, if you look at the number density of clusters, what the mass distribution is, that can tell you something about the initial conditions of the universe and all the evolving steps that have happened up till now. But also because it's at this node, you've got a lot of, the formation of structure, you've got a lot of things falling into clusters. It's a very different physical environment to, for example, something in the filaments or in the sort of the void areas. So that can have a very big impact on smaller scale astrophysics. So for example, formation of galaxies. So I know we're at a radio conference, but I think a lot of people will be still familiar with these beautiful composites that come up. Whenever we do anything in astronomy, you can't, no observing band is an island. You have to be looking at things in the multi-wavelength view. So here's a beautiful, I love this composite of the famous bullet cluster. And so here you've got, for example, in this case, optical and infrared telling you where the galaxies are. So it's showing, mapping out the intercluster light, what type of galaxies they are, etc. You've got the sort of the pink or the red showing you what's happening with the thermal intercluster medium. So in this case, Chandra imaging and the X-ray. And then you've also got in the blue telling you where the dark matter is sitting. And this is through gravitational lensing, in this case with Hubble. Now, when you add the radio view to this, so in green here, we're showing the MeerKAT observation of the same system, you can start probing the non-thermal intercluster medium, as well as cosmic rays and the magnetic fields. So what you'll see in this case is that for this particular cluster, you have the intercluster medium itself shining in the radio, but you can also pick up a lot of radio galaxies of differing morphologies. And that gives you a very different picture to, for example, something in another waveband we'll see. So that's what a radio observation of a cluster could look like. What would you do with your observations? So in many cases, so a single cluster pointing can be used for a variety of science. This is not an exhaustive list. And I'll leave, for example, there are a few AGN talks that I've seen. And Mary Lou has a poster on bent-tailed sources, so please do hunt her down if you have questions about those. I'm mostly going to focus in this talk on diffuse cluster radio emission because it's my main sort of area of study. I'll touch very briefly on star formation rates. I have one slide on it. And I'm pretty much not going to go into cosmic magnetism at all because I just don't have time. But please come chat to me. And there's also, I've seen some POSSUM posters a lot, so there are some polarization people who may deal with cluster environments. So diffuse cluster emission, what is it? So when I say diffuse cluster emission and I say large, I'm talking about things on scales of a few hundred kiloparsecs to megaparsec or more kind of scales. They're all faint. So by faint, I mean microjansky level at the gigahertz frequency. They're steep spectrum, which means that they're brighter at low frequency, and they're rare, or at least initially we thought they were. So here we are looking at synchrotron emission. So you have to have, two ingredients. You've got magnetic fields and you've got relativistic electrons, moving through the medium. So what makes these sources interesting is that the scales that we see them on, the volumes, cannot be explained by normal timescale arguments. And there has to be something happening that keeps the electrons at high enough energy over the volumes that we see the emission cover. So in diffuse cluster emission, currently we have these main different classes. They're separated mostly in terms of morphology, where they lie in the cluster, are they polarized or not, and also in the dynamical state of the system. So for example, the one on the left, radio relics and radio halos, these are the largest types of sources, and they are linked primarily with, well, almost exclusively with disturbed clusters. Whereas mini halos in the center, we tend to find them in cool core systems where the mini halos around the brightest cluster galaxy. Now, all the things that we know about diffuse emission so far, this field has boomed over the last 20 or so years. We get information through two ways: really good individual studies and statistical samples. So this is an example of one of the sort of the poster children of radio relics. This is the toothbrush relic. I really love our cool names, but you can see why it's got it. So this was first published in 2012. And when you have individual studies, you're looking at a particular source that is typically large enough on the sky that it can be really well resolved, and it has to be bright enough to be able to see over a wide wavelength. And also typically for radio, well, at least for the diffuse emission studies, most of our poster children lie in the Northern Hemisphere. And this is kind of, I would say, historical, because that's where we've had the widest variety of telescopes in terms of resolution, sensitivity, frequency, etc. So why I say individual studies can give us so much information is, so this example, as I said, first paper was in 2012. Since then, it has over 10 papers that are just getting new data on the system. When I looked on NASA ADS, I saw at least 30 or more papers that reference the source in the abstract. So in terms of using information generated from data on the source to infer and move forward our understanding of, in this case, relic emission. So for example, you've got people following it up with polarization sensitive studies, very wide spectral studies. So the spectrum that you can see in the middle bottom, here you're covering 2 orders of magnitude in frequency. And this can really help you understand the electron populations that you're dealing with. And then you've also got modeling. For example, if you know a system really, really well, you can start playing around with different modeling parameters and really trying to get a grip on the formation mechanisms that are creating this particular source. And we hope to infer that these individual sources, we hope that they represent the general population. So the other thing, obviously, when you're looking at a source a lot with many different telescopes, you get a variety of information. So for example, if you look at the same object with different frequencies and similar resolution, you are nailing down the spectral behavior, not only in an integrated spectrum, but also in spectral mapping. So I don't show a spectral map here, but basically you can start spatially resolving where different electron populations are. And then also if you just are looking at the same frequency, but you now look at it either with different instruments, or for example, the VLA gives you, or interferometers basically give you a lot of flexibility in the resolution and the UV ranges that you're covering. You can resolve out much finer features which tell you about the localized happenings, but also the global sort of volume of the source. But obviously not every source out there is suitable for an individual study. They're not bright enough necessarily, then maybe they're not large on the sky. Maybe a lot of the telescopes can't see it, historically, for example, stuff in the Southern Hemisphere. So this is where statistical samples are really useful, and they kind of give you the information about the global properties. And if your statistical samples are big enough, you can start looking at evolutionary trends between different parts of the space. So one of the first statistical samples, well, historically they were using X-ray selected samples of clusters. And one of the first things that came out of it was that there was this apparent dichotomy in terms of you had detections that lay on a correlation, and then you had clusters which didn't show any diffuse emission. So in this case, I'm talking specifically about the giant radio halos, and that your upper limits were sort of an order of magnitude below the correlation, at least at the high mass end. And this was quite interesting because one of the formation mechanisms that were sort of being floated around at the day actually predicted this sort of bimodality. So again, samples letting you really nail down the physics of what's happening. But it's never that simple. So when people started looking at cluster samples detected through other methods, so for example, looking at Synev-Zeldovich effect, clusters looking at through that. So for example, Planck ACT SPT, and looked at the same sort of plots. We still saw a correlation. That's great. So the radio is still correlated with the cluster, the properties of the host cluster itself, but this bimodality seemed to be disappearing. So now that leads to questions of, is the bimodality real? Is it just a selection effect? And what are we not understanding here? And then to further muddy the waters, as more observations were taken, instruments got more sensitive, we started observing sources that we call ultra steep spectrum. So these, they really just drop off at gigahertz frequencies, and these are the ones in green, and they can, particularly if you move, look at the left-handmost plot, they seem to be filling in the space between the correlation and the upper limits. Again, leading us to question, what are we still not understanding in terms of our formation mechanisms that we still need to improve? So again, I mentioned for radio halos, they are linked with, they seem to be linked with the dynamics of the system, or at least our formation mechanisms require some sort of energetic procedure to be taking place. So one of the things you can naturally do is start looking at the radio versus a tracer of substructure. So in this case, this is X-ray determined. So this is from X-ray imaging. You can get some morphological parameters that are probing substructure in the line of, in the plane of the sky. The shaded region here I've just highlighted is where we nominally would consider a dynamically disturbed system to sit. And we can already see that, there is a trend. You definitely have more detections in disturbed area than you do in the sort of the relaxed area, but it's not perfect, right? It's not clear. The ones that are in the relaxed, so detect red points in the relaxed region might be able to be explained by maybe those merger activity happening along the line of sight, which the X-ray data is not sensitive to. But what's happening in the disturbed region? Why are we seeing clusters with obvious substructure that are in the right redshift, in the right mass as everything else, but they're not showing diffuse emission? When your statistical samples get big enough, you can start, as I said, you can start splitting things up into subsamples. And this particular work split things in mass. So I say low mass here. It's still not really low mass, but it's just the lower mass part of their sample. And there you're seeing different behavior. There's a much clearer separation where if you see a detection, excuse me, it's definitely an emerging system. Because one of the ideas we were playing around with in the earlier days is that can we use the radio to trace dynamical activity? So I've mentioned a few open questions. There are more. And again, the ones you see here are not the only questions, and they're only for halos. We still have questions about the other classes. But one thing that two things that I'd like to mention, first of all, is the dynamical state of the system itself might be influencing your scaling relations and scatter in your data sets. So it's really great simulations done, which essentially showed that depending where within the merger track you're observing the system, you'd expect to see very different radio emission. And that could mean that the same cluster could move from the upper limits onto your correlation and back off it. Which, ideally, if you were wanting to get a really good correlation, you'd want to have this merger state nailed down. This is very challenging because you need good multi-wavelength data on every system. And then the other thing is that the statistical samples that I mentioned before were restricted to high mass, low redshift systems, generally because this is where the emission is expected to be brighter. It was the low-hanging fruit. So what you see on the top right plot there, the shaded region is basically showing you the region of phase space that has been investigated with statistical samples so far. And if you think about a low mass system or a high redshift system being compared to the ones on the statistical samples, they can be very different physical environments. So the things that we see in the high mass, low redshift sample might not hold for these other regions, and we have to start exploring that. The first high redshift, we've been doing cluster by cluster investigations of high redshift systems, and one of the key findings was a very powerful diffuse emission in the El Gordo system, which is high redshift. It's 0.87. And the current formation theories just couldn't really explain that. We expect as you go to higher redshift, you've got the magnetic field of the cosmic microwave background dominating, and you shouldn't expect to see sources like this. Follow-up work was published in Nature by Gabriele De Gennaro and co-authors, was really interesting because basically what they found there is they looked at a sample of high redshift systems with LOFAR, and what they found essentially was that magnetic fields at high redshift are different to what we thought they were, and this has major implications for our formation theories. So that's all good, that's what we know so far, but moving forward, if we're going to move the field forward, we have to start looking at wider cluster environments, both in terms of the individual samples, studies rather, and in terms of statistical samples. And currently, the precursors and pathfinders have been doing a really good job. Obviously, I'll tell you at the end, it's not good enough, thankfully, otherwise we wouldn't have the telescopes we're here to talk about today. And I'm not going to go through all the work that's being done with these. It's a massive amount. If you're interested, I would really suggest you go look it up. LOFAR in particular has been doing massive strides in the statistical sample because of their low frequencies. I'm obviously going to focus on MeerKAT, and that's, I'm from South Africa. It's why I have a job, essentially. So for those who need a refresher, MeerKAT's got 64 dishes. It's currently operating in three bands, and it gives you several spectral modes. The key thing here is that it can see the southern sky with unprecedented sensitivity than what has been available before. And also, the key thing for diffuse emission, at least, is how they have placed the telescopes. So MeerKAT has about 2/3 of the antennas in a very densely packed core, which gives you really good sensitivity to this faint, fuzzy stuff that's large on the sky. But simultaneously, it's got long enough baselines that you can get good enough resolution to disentangle point sources from the faint large-scale stuff. If you just look at something with low resolution, you might have great sensitivity, but you can't tell what is just blended point sources and what is the signal you actually care about. So here's an example of this. This is Abell 3667. Previously, the best data that we had from it was from the SUMS survey. This is 45 arcsecond resolution. And when you look at the same source with MeerKAT, you really start resolving out fine detail, and you'll just have to take my word for it that you still get this large scale structure as well. You just can't see everything in this single image. So that's my pretty picture for the day. So that image that you saw was from the MeerKAT Galaxy Cluster Legacy Survey. There's a data release that came out at the beginning of last year. Basically, this was an observatory-led program for 115 galaxy clusters. It used over 1,000 hours of telescope time between 2018 and 2019. They're typically deep observations, so you're getting about 4 microjansky per beam sensitivity at 8 arcsecond resolution. And it's a really great sample, but it's heterogeneously selected. So in terms of statistical studies, it's probably not the greatest, but it has already told us a lot of new things. So as I mentioned, there's a public data release. I'm not going to go through the details. This is for perusal afterwards, or please come talk to me. But the key things, the data is there, and it's proving to be quite useful. The main capabilities I want to mention here, obviously, it's polarization sensitive, at least for 40% of the first data release. And MeerKAT is giving us a lot of sensitivity to, on many scales. So you can do these games with your UV coverage and your visibility data, which is something that I'm a little bit worried about for, when we don't have visibilities moving forward. So in terms of what was found, you saw this source earlier, but in terms of diffuse emission, there were, of the 115, about 54% of them had some sort of diffuse emission detection, totaling 99 sources. About 50 of those were new, had never been seen before. And even the systems where we knew there was some sort of diffuse emission, we were starting to see probing a different picture. So for example, this Phoenix source in the image in the top right, here you can see, so both the blue and the yellow are both from MeerKAT, the same observation, and there you're probing both the full volume of the source as well as the finer details of the filament theory structure. And then, as was always exciting, it was also showing us stuff that we just can't classify right now. I don't know what this thing at the bottom right is. If you have ideas, do come talk to me. But the morphology doesn't fit in any of our classifications. Maybe we have to revise things. Maybe we have to go back to the theory. Maybe this isn't even the type of emission that should fall into this classification. It needs more study, but that's why we get excited. And then just a brief thing on the polarization side, one of the really nice things that came out of the data on Abel 3667, work by Francesco de Gasperin et al., is that we were able to start probing the 3D polarization structure of the relic, which I think is the first time this was done for diffuse emission. And this is quite sort of groundbreaking in terms of what's happening with the physics. Going back to well-studied systems, we're still learning new things. The bullet cluster has been observed before, and the dashed circular region is where we thought the halo lay. Really good quality observations from, I want to say the VLA, but I might be wrong. But either way, that was it was really good quality data. We thought we knew everything about the system. MeerKAT looked at it, and we're seeing a much more extended north-south part of the halo, which is actually now filling the X-ray emitting region, which is really cool. Obviously, we see more emission than we thought there was, so maybe we need to revise what we thought was happening in the system. But it also lets you now do things like point-to-point correlation studies, which is the graphical plot that you see in the bottom there, and the slope of the correlation between X-ray and the radio, or it's basically a thermal property in the radio. The slope of that can tell you something about the formation mechanism. So in the case of the bullet, it had quite a linear relation, and this is telling us that it's predominantly reacceleration processes that are happening. So my quick nod to star-forming galaxies, it's a cluster observation, but in many cases, first of all, there's lots of other things in the field other than the galaxy cluster, because MeerKAT has quite a large field of view. But in the cluster itself, you can study the galaxies instead of the intercluster medium. So this was work done by a then PhD student, now doing his first postdoc, where he was looking interested in looking at the star formation rate and the effective environment. And he actually separated his sample. He took a well-selected subsample from MGCLS, so looking at Atacama Cosmology Telescope clusters. And what I want to draw your attention to is the middle plot, where he separated systems into ones that did and did not have large-scale diffuse emission. And he's seeing a very different trend in terms of, as you go further out from the cluster center, the clusters that don't have a radio emission, so we think they're relaxed, you get a very different trend to where you've got dynamical activity happening. So that's the sort of the survey where individual pointings are going to be really, really useful. We might find more poster children or just different poster children that maybe explain a different part of the sample. We're also trying to use MeerKAT for statistical studies. So the mergers survey is something that I'm leading, where before SKA comes online, we're wanting to start foraying into these wider selection regions. So higher redshift, potentially lower mass, where we're really starting to want to look at evolution studies, both for the diffuse emission, but also for the magnetic fields. So when you have a telescope with a limited lifetime like MeerKAT, you have to, and you want a large enough sample where you can play these games of splitting things up into subsamples. You can't ask for infinite time. And one of the things we sort of considered from the beginning is that we might have to do this in short telescope tracks. MeerKAT's really sensitive, so this was viable. Thanks. But when you have short observation time, you can have potentially other issues, like you don't have sufficient UV coverage, we can mess with your PSF and mess with your ability to create a science-worthy image. So we did a pilot study of 13 clusters. We purposefully biased it towards likely mergers because we were really trying to find the diffuse emission and more or less test our observation strategy rather than get out sort of key science. We got science out anyway, which is great, but the main thing is like, yes, it worked. We managed to, take high quality images so some of the images that you see here are using only 30 minutes of telescope time. I think we went up to an hour and a half in this case. And the detections that we got, we are happy that we're actually seeing all of the emission. So this gave us a good sense that we could actually start going after a statistical sample. And the first one we've selected is in the redshift range 0.4 to 0.6. This sort of mid to high redshift range really hasn't been probed before in terms of statistical studies. You can see the addition there on the mass redshift plot of where we're talking about. And if we build up the sample, we can start cross-correlating with the lower redshift sample rather, and at least start going after cosmic evolution. This is preliminary. We're still waiting for some of our final data to get taken. Should happen this month, I think. But it's looking good so far. We've got about a 40% detection rate doing sort of just eyeballing our SDP images. So hopefully we'll have good results in a couple of months. You were working so well. There we go. And the last thing I want to mention in terms of what's coming out of MeerKAT at the moment is really exciting stuff. Again, these are individual studies, but when we talk about extended ranges, we have 2 teams that have looked at high redshift clusters, so that's above a redshift of 1, and they've found halos in this case, or what is very likely halos, which would be the highest redshift halos ever seen so far. And then also in terms of the low mass regime, we followed up one of the JWST science targets, and lo and behold, we've got an almost megaparsec scalar halo in there, which is, in X-ray at least, quite a low mass system. So with SKA and ngVLA, I think they're going to revolutionize what's going to happen. It's going to give us really good wide spectral ranges. So in terms of well-sampled spectra, these are typically those poster children. We only have a handful that have been studied over a wide spectrum. Hopefully this will now become the norm. And it's going to really allow us to probe this full range of the cluster environments. And then, as always, there's stuff that we don't know yet that SK is going to reveal. And I think that might be one of the most exciting points. So just to summarize, MeerKAT's doing really good work. It's not the only player in the game, but so far what's coming out of it is really exciting. But looking towards the SK and the ngVLA, there's a lot to come. There's some work to do in terms of how we're actually going to manage the usual things people have spoken about, data volumes, etc. And then I just want to highlight the fact that MeerKAT will be 5 years old since its first science paper, beginning of next year, and we're holding a meeting. So please look out in emails for that blurb. Thanks.
Thank you. Any questions for Kenda? Okay. Any questions online? Thoroughly explained. Thank you. That was so MeerKAT's really evening the score then in the Southern Hemisphere. Then.
Yes.
Yes. Excellent. All right. Lunch sleepies. Okay. Yes, I've got a question. Wait for a microphone. Here we go. Oh, right down here. To your left.
Thank you. That was a great talk, very inspiring for after lunch to keep us awake. And just a really banal question. Will the meeting that you're having be accessible remotely?
We are still having those talks. We hope to. So at the moment, it's going to be in Stellenbosch in the Western Cape. So internet connection should be good enough.
Okay, throwing one hope. Thank you.
Sure.
Toby in the back that way.
Thank you very much. I can probably get this information from the paper or the website, but I was wondering about the depth of the H1 observations for the cluster galaxies, or the H1 science. So basically, a lot of the interesting quenching questions are for galaxies that have lost their H1, or have low levels at least.
Sure. So I'm admittedly the wrong person to be asking about H1, but so I will. The caveat with MGCLS is that it was not designed as a spectral project, so it's only 4K channel mode. So Mpati, who's unfortunately not here, she's on the organizing committee, she led a lot of the H1 work. So I'm not sure about the depth. I'd be able to pull it out the paper, but the point is that it can be done, but only for the sort of, I think they've focused on clusters below redshift of 0.01 or something.
Right down here, Joe.
I don't think said much. Did you say anything about CRISM, the reboot of the Japanese mission that was going to look at how wide the X-ray spectral lines were and what the state of the intercluster medium is?
No, because I have never heard of that before. That I'll have to come talk to you.
Very good. All right, let's thank Ken again.